Let's see what happens. Oh, okay, got it. Something is happening, at least. I see attendees showing up, so that's good.
Hello, good afternoon.
Hi, Shenwei Chen from University of Waterloo. I see you just entered as an attendee, and I've just promoted you to a panelist. I don't know if you have to go and accept that invitation, but it's important if you want to, as you want to share your presentation. And yeah, I see you just entered as a panelist. Good. I might look out for more of our panelists in the attendees list. Okay, good. Hi, everybody. It's 2 minutes past 2 here in Europe, in Copenhagen. Good to see you. Good morning to some of you and good afternoon to you in Europe. I'm just going to wait a couple of minutes to have a full overview if all our panelists are here. I think they are.
Where's the rest of the team?
Shenwei, I hear you talking. Maybe it's not the best sound. Maybe you can just try to, can you say hello? I need to know that your sound is good. Shenwei, hello?
Hi, good morning. Yeah.
There you are. There was a little noise in the background, but I think I hear your voice clearly now.
Sure. So shall I just mute?
Yeah, that's good. I see 3 of you in the panels list, but yeah.
Yeah,
as
yeah.
long as you are able to
Sure.
follow. Okay, good. Should we just proceed? So hi everybody and welcome and thank you for joining this AutoICE Challenge Winners event. It's the formal closure of our AutoICE Challenge that we have hosted on the AI for EO platform together with the AI for EO consortia partners. I'll present them just in a few minutes. I'm happy to see at least we have 12 attendees, I think more registered, but we'll just go along, and me and Andreas from the project team or the organizing team will present just a brief overview of what the challenge was about so that everybody who was maybe not a participant in the challenge or forgot what it was about because it started back in November. We just want to take just a brief overview of the challenge and how we did the parameter selection and included the expert team and the metrics for scoring and such, so that we are all on the same line when we are to listen to our top performing teams that are here today for presenting their winning solutions. So we'll have the winning teams number 1 and 2 presenting to us. Before we have a short break, and then after the break we have the team that had the 4th place in the AutoICE Challenge presenting, and then we'll have a wrap up at the end. And I hope you're interested in posting some questions. We have in the chat. Please post if you have questions, you can write them there and make this protocol where you do slash the name of the presenter if it's a question to one of those presenting teams, or if it's for us, the organizers, then you can write to the organizers. And we'll try to answer those questions as we move along, or else I think there will be some email correspondence, contact information on the slides that if your questions are not answered during this event, then please get back to us, get in contact with us. We are very interested in your questions and comments, and also to you participants out there, if you have feedback on how the challenge worked and the data sets and tools and such, then please get in touch. Okay, next slide, Andreas. Maybe I'll just say that I had some presenters, they suggested that they might have a little short presentation, so we might be a little early. So don't keep back your questions, just push them, else we'll finish a little early. Okay, for the AutoICE, so just recalling the aims of the challenge. I don't see, Andreas, oh, there they go. Thank you. Okay, so the aims here of the challenge was from us in organizing. We wanted to work on improving automated high-resolution CIS parameter retrieval from SAR imagery, some synthetic aperture radar imagery. Many of us in the organizing committee work with this theme ourselves, and then also a discussion with ESA, who is also funding this project behind the AutoICE challenge. They wanted to have us push from single parameters so there's a big effort in this AI for CIS community towards prediction of CIS concentration or ice and water discrimination. So we wanted to, with this challenge and with the data sets, to push towards multi-ice parameter retrievals and people looking into solutions of this, maybe multi-task models and such. We don't know for sure because we haven't seen the solutions presented yet, so we are very eager to see how people solve this. Then also we wanted, with the preparation of the training set data sets we put available, we wanted to move towards a more pan-Arctic generalization with including ice charts from more ice services. So in the training data set, we have ice charts or label data from both the Danish Meteorological Institute that produce ice charts for Greenland area, and then also from the Canadian Ice Service that produce ice charts over the Canadian archipelago, Canadian waters, and also part of the Arctic Ocean. So maybe it's not pan-Arctic generalization, but at least we're trying to move this community from predictions that cover national area of interest towards a more pan-Arctic coverage. And then, of course, we wanted to engage with you that also signed up for this, for the challenge and for this webinar. I don't know if it's a settled term, the AI for CIS community. We used this before at some Feed Week session events and such, but I hope that this challenge had engaged more people in this area, and that we can expand this community and that we can all gain from it with these presentations and communications and discussions back and forth. At least that's our ambition from the organizer side, that we really want to engage with you and move this forward, bringing these tools and models and paper submissions into this field. And then, not least, make these tools and data sets available. Those tools and data sets that have been prepared for the challenge are still available and will be continuously available to you, so that you can, if this was just an appetizer for you, still wanting to work with this field, then these things are available for you to continue your work. And we made the different versions of these data sets to lower the barrier for entry into this field. And I hope that's what happened, that people thought it was easier to engage with this CIS domain. Next slide, please. So this is just like saying, who are we that are behind this? Maybe you see us at the list of panelists, attendees. The AI for Arctic project is an ESA-funded project, and that have designed this challenge and the metrics and the parameters and all that. It's led by Rune Solberg from the Norwegian Computing Center. And then we have Andreas Stockholm with us today. His colleague Roberto Santos is not here, unfortunately, but Andreas is from the Technical University of Denmark. He'll present in a minute. And then we have Anton with us, I hope. we have him with us. That's good. Anton is also part of, he's from the Nansen Environmental Remote Sensing Center, also a sea ice expert. And David Arthurs from PolarView, kindly supporting with the resources for computing and such for this challenge, also in the sea ice field for many years. And then my colleagues Tore, Jørgen, and I, Mathilde Kreiner, we are from the Danish Meteorological Institute, contributing also to this with the data set generation and such. And then we had very nice support from the AI for Your platform, and from Fernando is here today. His colleagues Jon and Anne-Catherine from Space Tech Partners also supported us very well. All our requests and submission problems and all that, really nice help. Jacobo and Joanne also helped us with metrics calculations and all that. So it's been a pleasure working with you guys. And thank you, Fernando, for helping us host this event today. Next slide. And then I wanted to present the AutoICE expert panel. These guys have volunteered to help us with designing the challenge. So we asked them. So it's Martin Rogers is here today. He's a research and machine learning expert from the British Antarctic Survey. And Martin and Nicholas from the ESA Field Lab, those are the machine learning experts in our expert panel. Then we have Nick Hughes from the Norwegian ice service at Met Norway, and next Tom Sagan, who's also a CI scientist and working with the Canadian Ice Service. And they were appointed and volunteered to join this expert panel, appointed by the International Ice Charting Working Group. So we are happy to have the International Ice Charting Working Group endorsing this challenge in that way, because we see also the ice services as a natural, what can you say, user or interest group of these evolutions and what we can do with this AI for sea ice and automated sea ice retrievals and such. So Martin, Nicholas, Nick, Tom, and also Jan van Rijn from Leiden University unfortunately couldn't be here today. These guys has helped us in designing the challenge, selecting the sea ice parameters that we wanted to predict, and also setting the metrics. So we had a jury workshop where we settled all these things before designing and putting up the challenge on the AI for Your homepage. And these guys are also here today to ask nice questions to the presenters together with us in the project team. So we're really looking forward to hear your solutions in a minute. So thank you to the expert panel for also showing up here today. Next slide. And here we have the main persons of today's event. So congratulations to the winners of the AutoICE challenge. So after closure, we did the last calculations on the private leaderboard. It's still open and available. You can go and have a look at the scores there, and we also copied them in here. So first place are the Waterloo University teams. There were multiple teams from the Waterloo University lab, and they together won the first prize in this competition. So they are represented by Xinwei. Today he will do the presentation of their solution. Had a very nice score. And the second place, we have the PVGSN team here today. I don't know what that stands for, maybe, but you can enlighten me in your presentation what that stands for. And also with a very nice close score. I think it's amazing how in a short time frame of this challenge we had very nice results, or you had very nice results, you the winners. On the third place, we had the CRISI team. The CRISI team couldn't be here today to present their solution, unfortunately. But at the fourth place, the SIM team, today we have David Rygerstam here today. I tried to pronounce it correctly, and he will do a presentation after the break of his solution. In the fifth place, we have the JFF team. I wouldn't know what that stands for. Unfortunately, this team couldn't be here today either. So 3 of the winning teams, top 5 performing teams, will be here today to present. And with this said, I'll give the word to you, Andreas, and you can walk us through the challenge design, metrics, and such.
Thank you for that, Mathilde. Hello, everyone. My name is Andreas Stockholm. I'm from the DTU Space, which is the National Space Institute, part of the Technical University of Denmark. As Mathilde said, I will give a brief overview of the AutoICE challenge and explain why sea ice charting is important, so we're all on the same page. To navigate quickly and most importantly safely in the ever-changing icy waters in the polar regions, ships utilize sea ice charts, which are maps of the local sea ice conditions. and that are still to this day created manually. The maps are mainly produced based on radar images acquired by satellites because of the large coverage, high image resolution, and versatility to measure independently of clouds and sunlight. Sea ice is in constant motion, and because of this dynamic nature, ice charts are drawn daily. This is a resource and time-consuming task, which we challenge students, sea ice, machine learning communities to help find a supervised deep learning solution to in the AutoICE competition, using these sea ice charts as label data. Participants were tasked with developing models capable of producing the three sea ice parameters, the total sea ice concentration, which describes the ratio of sea ice to open water in 11 classes of between 0 and 100% in discrete increments of 10%. Then there was the stage of development, which is the type of sea ice and is a proxy for the age and the thickness of the ice, and there's 6 of these classes. And then finally the flow size, which describes how large flakes of ice are, and this is in 7 classes. These ice parameters are extracted from the polygons in these ice charts. The ice conditions are described in the EC code for each polygon, with the primary descriptor being the total sea ice concentration. In addition to this, there are partial ice concentrations which sum to the total sea ice concentration. And for each of the ice concentrations, there's an associated stage of development and flow size. Here, polygons for the stage of development and flow size we have only used those if the partial ice concentration is dominant in the polygon, which we have defined as being equal or above 65% of the total sea ice concentration. And this is to avoid any ambiguous polygons. So participants have been provided with a data set, including 512 training and 20 testing scenes, covering, as Matita said, the Canadian and Greenland Arctic, with charts produced by either the Canadian or the Greenlandic Ice Service, respectively. And each of these scenes contain 2-channel dual polarized horizontal and horizontal-vertical Sentinel-1 images, the radar measurement incidence angle, the distance to land for every pixel, microwave radiometer measurements from the AMSAR-2 sensor on board the JAXA GCOV-V satellite. Then there was several numerical weather prediction parameters, such as the temperature and so on, from the ERA 5 reanalysis datasets. And then the aforementioned corresponding ice charts, of course. Furthermore, 2 versions of the datasets were created to cater to both the ease of getting started, while simultaneously allowing those who prefer fully customized models training setups to pursue their ideas. In addition to the dataset, software was provided to the participants to help getting started working on the challenge quickly. And computing resources through the Polar Thematic Exploitation Platform, also known as Polar TEP, was available, also with the data already there. For the challenge participation, we saw a continuous influx of users with fewer registrations towards the end of the competition. That kind of makes sense. In total, we had 129 teams and 179 users registered on the platform. For submissions, participants started delivering their test solutions around halfway through the competition, with a peaking submission rate around the end of it. And in total, we received 494 submissions and 34 from 34 different teams. So how did we evaluate the participants? We composed a testing set of 20 scenes, as I mentioned earlier, with all the ice classes present that were in the dataset, on the training dataset. They were taken from diverse, the scenes are from diverse areas with various sea ice SAR signatures, and charts from sea ice charts from both the Canadian and Greenland ice services. And the data, the reference data here should be available tomorrow for those of you who would like to look at that. Participants were asked to provide their model outputs for all 20 scenes so we could compare them with the labeled ice charts. Participants were then scored using a combined metric that was based on a weighted sum of a metric for each of the sea ice parameters. The sea ice concentration was evaluated using the R2 score, which measures similarities between two sets of data and excel at capturing the regressional aspect of the concentration. The stage of development and flow size were evaluated using the F1 score, which is a more classic classification metric. Each score was weighted with more emphasis on the sea ice and stage of development. On the online leaderboard, two scores were computed, one public and one private. The public score was computed on just half of the testing scenes, and this was available throughout the competition, while the private score was computed on all the 20 scenes and have just been made available after the closure of the competition, so that we could evaluate the participants on scenes that they had not received any feedback on. Then, as Mathilde mentioned earlier, the overall winners of the AutoICE challenge is the combined University of Waterloo team with a top score of 86.4%, followed by PWGSN with a score of 82.5%. On third place, we have Crazy with 81.2%, Sim at 80.61%, and then finally we have JFF on 80.56%. University of Waterloo further scored the highest on both the sea ice concentration and the stage of development, while PWGSN managed to achieve the highest score on the flow size and was the only top 5 participant to score higher on the flow compared to the stage of development. Overall, from the average scores that we can see here in the bottom, we can see that the sea ice concentration was the easiest to achieve high scores on, or the highest scores on, followed by the stage of development, and the flow size was clearly the most difficult. And with that, I think I will give the word to the University of Waterloo to present their solution, which myself and the project team are very eager to hear. So I'll stop here. Thank you.
Thank you, Andreas. Then, Xinwei, are you able to share your slides?
Sure.
And welcome. And nice to see many of you there. Good. Now we see all of us.
Yeah.
The whole community.
So I hope everyone sees properly.
Yes, looks good.
Yeah. Okay, cool. So thank you for giving us this great opportunity for presenting our solutions. My name is Xin Wei. So I'm a postdoc at the remote sensing team at the Vision and Image Processing Lab at University of Waterloo. So my presentation consists of the following parts. First, I will give a quick introduction of our teams, and then followed by a quick look of the background of this competition and our research. And then I'll go a little bit detail into our methodology, along with result analysis and some discussions. And finally, the conclusions and outlook of this work will be discussed. So as I mentioned, we belong to the VIP lab from the Department of System Design Engineering from Waterloo. And so the research interest of our group mainly lies in a broad area covering remote sensing, machine learning, computer vision. And specifically, we are very interested in the research of remote sensing of sea ice using SAR and other satellite data. And also we have done some research concerning hyperspectral image processing and aerial image processing as well. So I'm the team lead of this competition, supervised by Professor Clausy, Professor Scott, and Professor Xu. And we also have a lot of team members, including the postdoc and graduate students, as listed here. So a quick look of the background. So I believe many of you are experts in CIs. And so as we know, compared to the manual operational CIs mapping, the automated CIs mapping from SAR data and other satellite data has many advantages. For example, it will greatly improve the efficiency of the CIs mapping and also increase the resolution, because the manual CIs mapping is based on polygons that cover a large area. And also the CIs mapping from SAR data will have a wider coverage as well. And that will facilitate the research and many activities in the polar regions, as mentioned just now. So compared to some traditional algorithms or machine learning algorithm, the deep learning based approaches have many strengths. For example, you can automatically extract many deep features from the satellite data. Also can improve the accuracy and robustness given a large data set. So from the last 2 decades, our lab has done many representative works in CIs mapping. For example, we have developed a map guide AutoICE classification system. And also we are the first group that applies deep learning methods such as convolutional neural networks to CIs concentration estimation using SAR imagery. And also recently we have also done many research by developing deep learning based methods along with uncertainty estimation from CIs concentration and ice water classification. However, there are still many challenges given, although we have done a lot of research. For example, so one of the main problem is that the label samples the number of label samples are very limited, which I think will pose a negative effect on the generalization ability of our models. And also many of the current research relies on single source data such as SAR imagery. So as we know, the SAR imagery has many ambiguities in distinguish like ice and water and also different ice types. So it is important to develop methodologies that using multi-source satellite data to further improve the generalization and robustness of the models. So, so as we know, the Arctic AI for Arctic AI's challenge dataset provides more than 500 SAR-SIN, which is a large volume of data that covers large areas in the Arctic in different months, which is, I think, very suitable for developing the deep learning based model for CIs mapping. And also we have corresponding ice charts as reference of labeling. And also we have auxiliary data from passive brightness temperature data from AMSR2 and Earth-5 that have atmospheric data. And so the motivation for our participation is to push the boundaries of the AI-based CIs mapping and also promote the international connections and collaboration among the CIs community. Also, by participating in this competition, I think we will have a good starting point for our future research based on large data sets and the deep learning methods. So now let's move on to the methodology. So it consists of data preparation, feature exploitation, model design, the design of the training scheme, and also the implementation. So for the data preparation, since the organizer have provided us both raw and ready to train versions, so actually we can, so here we mainly rely on the ready to train version to expedite our model development, and it's kind of faster to process and implement. However, in the future, I believe we will further exploit the raw versions to have more processing step for the data. And so we, so from the codes provided by the organizer, we are able to incorporate multi-source data as combine them into the input channels for our deep learning model by techniques such as upsampling, and it provides us how to convert the ICE chart into polygon or pixel-based labels, and also those subgrid variables such as the brightness temperature have been upsampled to the size of the Sentinel-1 SAR imagery. So it's very convenient for us to process. And before inputting those channels into our model, we apply a technique called downscaling. So it's pretty straightforward. We just, as we know, the size of the SAR imagery for the ready to train version is around 5,000 times 5,000. So if you input, so we first downsample this size to like 5 to 10 by 5 to 10. So the input size of the model is around like 1,500 to 1,000 pixels per site. And so we did this because we will have a larger receptive field during training, because we select a fixed input patch of 256. So in that case, we can learn the contextual information from the SAR scene. And then because although we have high resolution on SAR imagery, however, the ICE charts provided the resolution is kind of low, relatively low. So to maintain the consistency between the predictions and the low resolution of the ICE chart, so we apply this downscaling to have a better visual consistency between our prediction and ICE charts. And also we, of course, we divide our scene into patches of a size of 256. We also try other patch sites, but it did not show improvement. And we also apply some data augmentation techniques for our input patches, such as the random patch scaling, rotation, flip, cut mix, and so on. So now let's move on to the selection or exploitation of the feature. And of course, here is a list of the optimal combination of features that we select based on multiple try and errors. So of course, it consists of the dual polarized SAR scenes with incidence angle maps. And also we include the distance to length map. So for the brightness temperature data, we select the 18.7 and 36.5 gigahertz in both vertical and horizontal polarization. I think the main reason to select those two channels is because they're kind of have a higher resolution compared to lower frequency, and also is less affected by weather compared to like 89 gigahertz channel. And also we, by trying different combination, we found that by selecting a 10-meter wind speed, 2-meter air temperature, total column water, and total column cloud liquid water, those 4 features into our input channels will produce a better performance. And also, in addition to those features provided, we also incorporate the latitude, longitude, and also the month information of each scene as the auxiliary input channels. So I think we did interpolation of the latitude and longitude of each pixel, so that we have the same size of input channel for as those features mentioned above. So I think we found that it will improve the model, the accuracy of the model, and I think the reason behind this is because we, for the operational CIS mapping that produced by the ICE chart, the experts will rely on the time and location information of this SAR scene, and he can refer to his own experience for CIS mapping, not just relying on the SAR data, which has ambiguities. So we resemble this kind of process, and we name it as spatial temporal encoding. So for the model design, actually, we have tried different configurations of the model. Most of them are based on the UNet by trying different number of filters and different numbers of blocks for encoders and decoders. And we also try some of the other state-of-the-art model like swing transformers. But based on the comparison using the testing data set, we found that the current model, which I think is based on a previous work using AI for Arctic data for CIS concentration estimation. So we modified the number of filters for a bit, but we still use 4 blocks for the encoder and 4 for decoders. And we found that this configuration that consists of 32 and 32, 64, 64 filters for each of the encoder will produce a better result compared to other configurations. And we kind of increased the number of these from 16 to 32 because I think the main reason is that we have extra input channels. So it would be better for increase the number of these, the first encoder to have better performance. And also we also found that we have separate decoders for the 3 tasks, which I think will improve the performance for a little bit compared to a shared decoder. And also for the selection of the loss function, we found that by selecting the mean square error loss for the CIS concentration, it will produce a higher accuracy compared to cross entropy loss for CIS concentration, which is consistent with the previous work. And for stage of development and flow size, we use cross entropy loss for training our model. So here is specifications about our training scheme, which is listed on the table on the right. So including the optimizer using stochastic gradient descent, a learning rate set by 0.001. And we also, for the scheduler, we use this cosine annealing scheme to adjust our learning rate and a batch size of 16. The epoch length. So we set a total epoch of 300 to make sure that the model can converge. And so the number of epochs for the first restart for cosine annealing scheduler is set to be 20. So the learning rate will go down and go up after 20 epochs. And we set a downscaling ratio, as mentioned just now, as 10. And a patch size of 256. So for the calculation of the total loss, because we found that the MSB loss will produce a relatively large value compared to cross entropy loss. So to prevent the CIS concentration dominating the loss value, we assign weight of 1 and a weight of 3 for the following 2 loss for stage of development and flow size. Sorry, there's a typo here. And so for the choose of the validation scene, we select 18 scenes that have with acquisition time and location close to the testing scenes. So to ensure that we have a close relationship between the validation and testing accuracy, and that's very important for evaluating our model properly. So for the implementation, that's very straightforward. We use PyTorch along with many libraries. We have also tried to implement our models on a very popular computer vision library called MMCV and MM segmentation. However, we have met some issues during the training and we're still figuring out. And we use weight and bias, this platform for visualization of our training. And we train our model on the Canada's national high performance compute system called Compute Canada. And some configuration for the GPU and the memory use is this here. So in total, we submit more than, I think, 100 submissions for testing our models with many different configurations. So here, the one I mentioned just now is just one of the best model that have the best performance. So here is some visualization of the training. So from the validation result, we can see that we obtain the best combined score of around 91, with CIS concentration around 93, which is the best among the three, and stage of development is 92, and flow size is 85. So we can see from the training curve here, that's the learning, how the learning rate changes, and that's the combined score. It kind of stay relatively stable after like around 50 epochs. And also you can see the how the stage of development, CIS concentration, and flow size goes. So there are some fluctuations every 20 epochs, which is consistent with the change of learning rate. So here are some visualization of the results obtained from the validation samples, because we have ICE chart here, but we do not have for testing things. So at least here for some comparison. So for the second row here, it's our prediction. Third row is the labels from the ICE charts. You can see, so here are a few examples. So we can see for the CIS concentration on the first column and stage of development on the second column, generally it has a pretty good consistency with the ICE chart in most of the regions. As you can see, here are some examples. You can see, especially for the stage of development, it has a uniform ICE type distribution. And we also find that compared to using cross entropy loss for CIS concentration, the MSE loss can produce a more detailed results of CIS concentration. But if you use cross entropy loss, the result will kind of be more consistent, have a more larger polygons that are more consistent with the ICE chart, although the accuracy is a little bit lower. And we found that most of the misclassification happened between neighboring classes. For example, one of the misclassification, as you can see here for the flow size, the ICE chart here says medium flow, but some of the regions are misclassified as big flow, which is neighboring with the medium flow. Same thing happened for the ICE type. So now let's move on to the testing results. So we ranked the first on both public and the private leaderboards. So as you can see here are the statistics. So compared to the validation results that we obtained, we have a relatively small gap between the scores obtained from CIS concentration and stage of development. We can see the gap is relatively small, around 2%. However, there's a large discrepancy between the flow size score obtained from the validation and testing sample. For example, we obtained 85 here in validation, a 70, nearly 78 for the public set, and only 70 for the private. So because we do not have the ICE charts for reference so far, so we need further evaluation if they will be published in the future. Of course, we need some investigation into that. So here are some visualization of the result obtained from testing scene, which have, you can see compared to validation, they have a relatively close distance in time and space. So from visual observation, it has a good consistency with the SAR scenes on the left. So here are just some examples, visualization of our testing scenes. And so we also did many ablation studies by considering the effect of different factors on the accuracy of our models, such as the patch size, downscaling ratio, feature combination, selection of loss functions, model parameters, class-wise accuracy, and so on. So here we use our validation sets for validation, given that we have the extra labels. And we found that by selecting a patch size of 256, it will produce the best results. And it's kind of unclear why selecting other patch size like 512 or 768 have much worse result compared to 256. It's kind of a magic number, so we need further investigation. And we also found that selecting a downscaling ratio from like 5 to 10 will produce a relatively good results, but it's also data dependent. Like if you test on different data, the best downscaling ratio might be a little bit different. So despite the improvement in accuracy, downscaling of the input scene also improves the efficiency because we have a smaller input size. So here is a comparison of accuracy obtained from different combinations of features. And we found that by selecting a subset from the MSR2 and ERF5, so the specific subset is mentioned just now, so we'll produce the best accuracy compared to just select like the dual polarized sarsings or selecting all the features. As you can see here, there are some slight improvement, like around 2% on the overall score. And we also found that by incorporating the time and location information, the accuracy will be further boosted by around 1 to 2% in the combined score. So we also compare with models with different loss functions. And we found that by selecting cross entropy loss, we will produce the best for all the three tasks. If we select cross entropy loss, it will produce the best stage of development and flow size score. However, if we applied MSE loss for CIS concentration, it will produce the best combined score because it will significantly improve the score of CIS concentration. However, the score of stage of development will decrease a little bit. So maybe there's a trade-off between selecting cross entropy and MSE loss, so which need further investigation. We also try some modification like focal loss, and to see if it improves the overall accuracy or the class-wide accuracy. But so far we found that it may improve the accuracy of some classes, but do not improve the overall score. So of course we need further looking into that. Also try other losses as this here, but the result are still not as good as the combination as this in the red. So here is a visualization of comparison between using different loss functions. You can see that so for selecting cross entropy loss, we have more homogeneous polygons, which in visually is more consistent with our ground truth labels. However, for MSE loss, it will have a higher accuracy, higher R2 score, because I think the main reason because it's more, will produce more detailed results. And also there are some visualization of using other loss. The result looks generally well, but statistically, it did not show significant improvement on the accuracy. So here we summarize some factors that we think are important in the accuracy of the CIS mapping. For example, the downscaling of the input scene and also the selection of the patch size. And also feature selections with spatial and temporal encoding will also boost the accuracy. And also the design of the training scheme, we find that it will also varies in our testing and validation accuracy, because we are selecting the checkpoint that have the highest accuracy during the training. And also selecting MSE loss will boost the accuracy of CIS concentration. And also the selection of validation set is also very important, because we will have a better evaluation of the testing samples if we select the proper validation scenes. And of course, there are many things that we need further investigation, including the design of the model. That so far we found that deeper models or some more novel deep learning models like transformer do not show improvement, but it does not mean that the other models won't. So of course we'll look into that in the future. And also we found that the accuracy of some classes, they are not dominant. For example, like intermediate CIS concentration or some young ice or some flow size, they are not open water or big flow like medium or small flows. Their accuracy is relatively low. I think that's caused by imbalanced number of samples. However, that is not alleviated significantly using focal loss. So we need further investigation into that as well. And also, if we have, if in the future, the ground truth or the ice charts for testing things are available, we'll definitely look into why the accuracy of flow size in our model is relatively low. And also we will look into to develop new processing methods to produce ready to train data set, because we know that for the generation of the labels for stage of development and flow size, only polygons that have over 65% of a certain ice type or flow size will be selected, and the others are discarded from training. So we will think about how to utilize those polygons given the echo information. So so in conclusion, in this competition, we developed our own CIS mapping model based on deep learning from multitask UNet, and with some insight analysis by doing many ablation studies, and AI for RT dataset with more than 500 things, and corresponding ice charts and multi-source data are trained to ensure high accuracy, robustness, and generalization. So we managed to improve the accuracy of our model step by step by using a bag of tricks like downscaling, spatial temporal encoding, the selection of loss function, and the selection of validation set, and so on. So in the future, we will aim to publish the comprehensive version of our solution in a special issue in the Creosphere, and also we will try to develop novel processing pipelines of raw data and echoes. And we also like to conduct the feature importance analysis on the input channels and manage to apply our methodology to some new satellite data from sources such as the RCM. And also we strive to apply our methodology to the operational CIS mapping and data fusion in the future. So we would like to thank the hard work done by the organizer and data providers of this competition, which I think will contribute a lot to our CIS community. Also, we'd like to thank the computing resources provided by Compute Canada, and also the contributions, the insightful discussion and hard work from all of our lab members, and also the support and promotion from the department and the faculty by promoting our work and winning in the news of our department and faculty website. So here are some references of our work. So thank you very much for listening. So please do not hesitate to for questions. So, and you can contact me for further questions. Thank you very much.
Thank you very much, Shinwei, for very thoroughly go through of your approach, and thank you to your whole team. I just saw them behind you in your listening also. So thank you to all of you for participating and contributing to this very interesting results and approach. Yes, I see Andreas with applause. Okay, so I'll open the floor for panelists that wants to ask questions or comments to Shinwei and his group, or his lab mates. So I see Martin, go ahead. Martin Roger.
Yeah, thank you for that talk. Just copy what Matilda just said. I thought that was a very detailed discussion, particularly about the different data types that you input into the neural network. I was just wondering, did you consider class imbalance during the model training in any way? I know you talked in your discussion about the fact that there is class imbalance, particularly, for example, looking at CS concentration. But did you play with that at all in model development and incorporation into the loss function at all?
That's a very good question. So in the most of our competition, we spend most of time focusing on improving the overall combined score or the separate score for the 3 tasks. So I think at the very end, we just look into the class-wise accuracy and found that we have a kind of imbalance issue that, for example, for CIS concentration, we have relatively very high accuracy on open water or like very high ice concentration, but we do have relatively low accuracy on intermediate sea states, intermediate concentrations. And so we try like loss functions like focal loss that should have increased the accuracy of samples that are not dominant for those classes, but does not show improvements. But nevertheless, we found that those misclassification mainly happens in the neighboring classes. For example, if the ground truth is like 40%, then it may probably predict it as, if it's not 40, then probably like 50 or 60. So we think that this is acceptable in operational use. And also we have also created a new loss function called order cross entropy that will penalize differently based on the distance of these classes. So, but it does not show significant improvement on class-wise accuracy. So I think we need further investigation into that. I don't know if the other team members have something to supplement.
Some loss function like diversity loss did help improve the minority class accuracy, but it did not improve the overall.
It does. We
You're not
cannot
able
really
to
hear
hear
it.
that. No, can you go closer to the microphone if you are answering the question directly?
Okay, so we tried Tversky loss, which is known for solving class imbalance issue. But when we applied that and saw the overall score, it was not improved, but the minority class accuracy, it was improved for some of the classes. I hope you can hear.
We heard that. Thank you. Yeah.
Okay, yeah, thank you for answering those questions.
Thank you. We have time for one more fast questions before we go to the next presenter. Jørgen, do we have a?
Yes, I just noticed because we decided to include this distance map in the input data as well. It takes some computing resource to generate these layers because we have to derive them for each unique SAR scene because the geometry in each SAR scene is unique. So I just wondered whether you noticed a big gain in performance by using this this layer, or did you look at that?
Yeah,
Can you please repeat your question? I did not get your question.
I think it's about including the distance to land map, right? Whether it improves the accuracy a lot.
It was not significant. So, including the distance to map.
Again, we can't really hear you. If you're answering the question, then get close to the microphone.
So, including the distance to land map did not significantly improve the performance, or did not significantly
I
decrease the
didn't hear you that loud, but I heard you say that including the distance to land map didn't improve significantly the results. Is that
Yes.
correct? Okay, good. Thank you.
Okay, thank you.
Okay, I see Nicholas has a question. Okay, bring it on, Nicholas.
Yeah, no, thanks for the presentation. I'm just wondering, for the ablation study that you did, how is that accurate, and how is that dependent on the initialization of the weights and the network itself? I mean, how accurate are these numbers that you present on slides 17 and 18? Did you run several training to have some kind of average and ensemble of result, or is that just a one-shot training?
Perhaps I can take over that question.
Sure.
We mainly ran, so we ran different experiments. So we ran the model multiple times with different initializations, and then we did basically a confidence interval to see if the changes were significant. Some of the changes were not really that significant, but we still decided to include them since they did not reduce the performance of the model.
Okay.
Did that answer your question, Nicholas? Yeah.
Yeah. The sounds is not so good, but I think
No.
I catched what you meant. That's fine.
Okay, I think we'll jump on to the next presentation. We're a little behind per time, but no worries. We have also a break that we can use. So please, the next presenters are the second place in the AutoICE challenge, and Patrick and Michael, you will present this together. That's really nice.
Yeah.
So go ahead and welcome.
Could you please confirm that you can see my presentation?
I see your presentation. Yes.
That's great.
We see you.
So let me just start by saying that it's not going to be easy to follow this gorgeous presentation of this great team, but we're still going to try. And let me also start by saying that we couldn't be more different in like every possible thing, like the team composition, available resources, and our approach. So yeah, couldn't be more different. So I'm really curious about what would happen if we were to combine our approaches.
That's
All right.
really interesting. So
yeah. All right, let me start with the team introduction. So there's me, Patrick, and there's Michał, my colleague, also present here. As you can see, we love ice, but we love ice not in the scientific meaning, because we haven't been working with ice before, nor with the geoimaging of any kind. We met on the University of Technology in Warsaw, where we're pursuing postgraduate studies in deep learning. That's also where the name of our team comes from. The PWGSN is in Polish Politechnika Warszawska Głębokie Sieci Neuronowe, which just stands for the name of our university and the field. So, for think about us, we met on the university. We are both experienced data science practitioners. We haven't worked with the geoimaging before, and we are located in Warsaw, Poland. There is also our thesis supervisor, because we're making this competition work at thesis for this diploma. That would be Jacek Komorowski, PhD. So big shout out to him, and thanks for guiding us throughout this challenge. And if it's too much information to remember about us, you can just remember that we're cool. All right. Data preparation, and off to you, Michał.
Okay, so let's begin with a few words about the data that we have used in our models training. So basically, we have just used ready to train data, and including all 24 input channels that were available. So we didn't have done any kind of feature selection process. We have been rather limited in time and had rather little domain knowledge. So because of this reason, we decided to concentrate the most on trying different kinds of machine learning approaches that could lead us to build the best model as we can. We thought that there is a space to enhance model metrics by exploring raw data a little bit more extensively, but as we said, we were rather limited in time, so we just focused on machine learning. At the same time, we hope that we trusted that the neural network will do a kind of part of the job instead of us by extracting all the important dependencies that are existing in the data. When it comes to data exploration, the only analysis that we have done was checking how much the data is imbalanced. So as we can see on the chart, pixels representing open water spaces were much more overrepresented than the other classes. At the same time, imbalance between different classes describing the state of ice was also noticeable. So because of this reason, we decided to play around with different loss functions that can be a little bit more robust to solve this kind of issue. At the end of the day, we achieved the best results using simple cross entropy. We also had comparable results using weighted cross entropy, where we used as weights the inverse of shares of particular classes. And we had also good kind of good results using dice loss. Because of the fact that we had rather limited resources when it comes to GPU memory, we were also worried a little bit about the way in which we are selecting patches. In the code that we were supplied with by the organizer of this competition, it was done totally randomly. And because of this fact, we were a little bit worried that we may supply our model during the training with very simple examples like those patches that are consisted only of open water pixels. So this is why we started to think about different kinds of methods of how we can more wisely select patches during the training process. In the end, we came up with the best solution that was comprised of two steps. So the first step was iterating over scenes with a window of the particular size that we were going to use during the training. And then for each window, we were counting share of open water pixels. And basing on this value, have been assigning 3 different classes to each potential part that could be cropped from the scene during the training process. So the first class was just open water patch. Then we had water ice edge patch. So basically it was the one that was combined of both open water spaces and ice pixels. And then the third one was ice only kind of patch. Then on the right side of the screen, you can see a chart which is showing single iteration over scenes that we used as an epoch. And we were simply iterating over all the scenes that were available in training dataset. Then from each scene, we were randomly choosing one patch, putting additional rules that were that P patches should depict a boundary between ice and water. So there should be of the class water ice edge, and Q patches should be of ice label only. And we were the most successful with using setup of P equals to 20% and Q equals to 10%. Okay, the next one. And from the very beginning, when the competition started, we had to put some effort into making both the training and validation look a little bit more time efficient. So as I mentioned in the previous slide, we defined an epoch as an iteration over all scenes, once choosing only one patch from each scene available. Because of that, we were able to train different models in parallel on set of GPUs that we had that we could use. At the same time, we had to divide our validation data set into patches, and that was because we have been very limited in when it comes to GPU memory that we could use. And because of that, we were able to overcome these memory issues once experimenting with more and more extensive deep neural networks.
All right, back to me. I'll tell you a bit about the model architecture. So basically, the easiest way to get started on any kind of competition, really, but this one in particular, is to find some kind of pre-trained model for a similar task. In our case, this task is semantic segmentation, and fine-tune it. So it's pretty easy to do, but we need a couple of adjustments to fine-tune any pre-trained model, because this case that we're tackling here isn't very common. So for example, we don't have 3 usual channels, we have 24 input channels, and usually semantic segmentation is done on like real photos. So you have the red, green, blue channel. So we had to extend the first layer of any model to 24. And if we extend this first layer to 24 channels, then the pre-trained, the dictionary of pre-trained weights doesn't fit anymore. So we have to modify the pre-trained weights that you can download. The way we did it is we averaged the weights from the original 3 layers, and we just repeated it throughout the whole 24 original 3 channels, sorry. And we repeated it throughout the 24 channels that we do need for our competition. And we typically, when you get an encoder, because we mostly relied on encoder-decoder architectures, the encoder will have some kind of classifier head at the end, because encoders are often used as classifiers. So in our case, we don't really need a classifier head. What we need are the feature maps. So we can use the feature maps to upscale them later for on the decoder branch. Encoder's classifier doesn't necessarily need to be detached, because it can be used as an auxiliary loss. We played around with a couple of ideas for auxiliary losses, like classifying patches majority class or a number of classes present on a patch, but that wasn't very helpful for us. We didn't put too much effort into it though, so possibly there is some more good that could come out of it if we put some more work in. And decoder is easier to adapt, but it needs 3 output heads instead of the usual 1 output head, so like a minor difference. And let me also tell you that in contrast to the previous team, we didn't have much luck with the convolutional neural networks. So for encoders, we jumped pretty quickly to the transformer architectures. And we had most luck with the co-scale convolutional image transformers. We obviously aren't authors of this architecture. You can find the paper and the code repository on the bottom of the slide here. But it is a transformer kind of encoder. Why transformer? For one, it's because of the receptive field. So in transformers, receptive field at each location in self-attention covers the entire input space, since each token is matched with all tokens, including itself. And that's actually a citation from this paper that I'm linking to here. That's a very good read if anyone is interested. And also transformers are more adjustable. Like in the self-attention mechanism, the weights are dynamically computed based on the similarity or affinity between every pair of tokens. That causes transformers to be more flexible to model spatial configurations beyond fixed input structures. Well, that and the position encoding. All right. And another citation from the paper, code empowers image transformers with enriched multi-scale and contextual modeling capabilities. So basically, that's a pretty good model for what we're trying to do here. And there are 2 versions of code. There is a big code and there is a light code. So we use the light code. It has no parallel blocks. So it's like a very lightweight version of the model. It consists basically of a couple of serial blocks where image features are downsampled and processed in a sequential order, and a co-scale mechanism that maintains encoder branches at separate scales. We do want separate scales because we do want a couple of feature maps to be inflated by the decoder later. All right. And what the serial block does, it basically does three things. A serial block models image representations in a reduced resolution. So we downsample input feature maps by a certain ratio using a patch embedding layer. We flatten the reduced feature maps into a sequence of image tokens, and we apply multiple convolutional modules to learn internal relationships among image tokens. That's also a citation from their paper because they are the ones who designed the serial block here. I crossed out the class token because we didn't use a classifier head in here, and also I crossed out the connections to the parallel blocks that we didn't use. All right. And the decoder was a deformer network in a paper that's described in a paper, Improving Network Architectures and Training Strategies for Domain Adaptive Semantic Segmentation. So obviously deformer also, we didn't come up with it. It's a paper that's linked at the bottom of the slide. And we didn't even come up with the idea to combine code and deformer because it was already done in one of the Kaggle competitions for semantic segmentation. The Kaggle competition I'm referring to is also linked at the bottom of the slide. By the way, that was a big chunk of our approach, just finding similar competitions for semantic segmentations and trying out architectures that did well there. So it's not like vanilla deformer, like described in the paper, because we got rid of this like big chunk of it. It was done this way in this Kaggle competition too. So that's where we have it from. So this hierarchical transformer, we can see on the graph here, that's like code in our case. It has those 4 feature maps that get aligned by number of channels and by size. They get stacked together, concatenated, and then we need to fuse them together. And we changed this fusing module from like this fancy deformer context-aware fusion with depth-wise separable convolutions. It's kind of similar to ASPP layer, if you know it from DeepLab architecture. And we replaced it with a simple 3x3 convolutional 2-dimensional filter, like in the Kaggle competition. So to recap, before feature fusion, we embed each feature map to the same number of channels by a 1x1 convolution. We bilinearly upsample the features to the size of the biggest feature map, and we concatenate them. And for fusing, we use 3x3 convolutions instead of the depth-wise separable ASPP with different dilations. Now a bit about the training routine. So we used a couple of loss functions. Like Michał already mentioned, the best performing ones was either the hybrid between dice loss and cross entropy, the weighted cross entropy loss, the vanilla cross entropy loss, and a cross entropy loss with label smoothing. Label smoothing is when you change like the hard values of 0 or 1 to a bit smoothed out, or like 0.05 and 0.95. And one of the things we noticed is that the loss functions that try to address the imbalance between the classes, which we know there was one, tend to produce lots of false positives for the minority classes. So it wasn't very useful to use them. So in case of the weighted cross entropy and the dice loss, which both are aimed towards reducing the imbalances, you can see that lots of this like lighter blue color, this minority class gets detected, whereas it shouldn't be, as you can see on the ground truth. The cross entropy loss, especially with the label smoothing, tended to work best in our case, although the final model that we present, Michał will get to that in a moment, is actually an ensemble of multiple models with multiple loss functions. So we used like kind of voting mechanism to combine them together. Learning rate scheduling. We didn't use a scheduler, but we did the scheduling manually, where we started off the training with a higher learning rate, and once it plateaued, we reduced it to 10 times to a lower learning rate, and yeah, it produced the best results for us. As you can see in this case, for example, the lower learning rate increases the validation loss, but that's not always a deal breaker for us because our validation set wasn't very well aligned with the test set that we knew from the public scoreboard. So even though the validation loss was still increasing in here, it didn't reflect the test scores. And the train loss is still going down, which in this case can mean that the model was starting to overfit a bit, which is why we also needed augmentations. So when we tested simpler architectures before, like efficient unit, for example, augmentations weren't really needed because we weren't able to overfit the dataset. The models weren't potent enough. And if they're not overfitting, we don't need augmentations. But for transformer architectures, overfitting started to be an issue, which is why we used augmentations of 4 kinds. We used rotations, flips, slight distortions, and the multiplicative noise. Multiplicative noise comes from our literature review phase, where we discovered that the multiplicative noise is a common issue when working with SAR imaging. So it would be there, either we put it there or not. So it's best to teach the model to deal with that on the training set. And back to you, Michał. You are muted.
Yes, sorry. So at the beginning of the slide, I would like to mention that we had rather limited resources. So we had basically 2 GPUs that were about 16 gigabytes of memory. So because of this reason, it was obvious for us that we have to patch and test scenes before iteration. So the thing that we had to done was, as I said, divide each scene from test dataset into patches, then make separate inferences on each of them, and then combine those predictions into a single map somehow. So this originally resulted in having visible boundaries between patches in the outcome. We expected that prediction error tends to be higher, closer to the boundaries of a patch. So this is why we came up with 2 methods. First of them was patch overlap. So we basically had our scene divided into overlapping patches. Then once combining predictions, we pick up only the central part of the prediction to the final outcome. Additionally, we have applied mirror padding at the edges of the scene, so as not to degrade predictions, prediction quality at the edges of the scene. The second method that we were working with was smoothing. It was kind of similar method to the previous one. The difference here is that we do not only take the central part of the prediction of each patch into account, but we use a whole prediction, interpolating overlapping areas of patches by applying second order spline window function that you can see on the right side of the screen. What is more, in case of each patch, we have rotated it and mirrored it so that for each patch we produced 8 predictions, and then we have combined them together by reducing by averaging. And we hope that it will help us a little bit to produce a little bit the predictions with a little bit more, a little bit less variance. Okay, so I think that it's also worth mentioning that we have been working, trying different kind of patch sizes on the test dataset. Okay, so as summary, I would like to mention that totally we have trained 140 different kinds of models. We have been trying with different things like trying different architectures, and this is in fact the thing that has boosted our results the most. We have been also modifying those architectures that are written down here to different sizes and different variations. We have been trying different loss functions instead of those that I have mentioned before or Patrick has done. We have been also trying focal loss and ordinal loss. We have been playing around with different kinds of augmentations, assigning to them different probabilities with which they might be used during the training process. We have been playing around also with P and Q parameters once choosing patches during the training process. We have been trying different sizes of training patches. We have also implemented many unsuccessful ideas that we came up with. For instance, auxiliary loss, which we treated as an additional loss added during the training process. we have been trying to train models separately for different kind of tasks. We also use clamping inputs. Okay, so the next one. So by trying different training setups, we obtained several models that had quite similar values of metrics. Thus, we decided to make an ensemble of those models, and we did it by majority voting for the class for each pixel. By this means, we hope that we will reduce variance of predictions so that we will be able to make it a little bit better on the private release scoreboard at the end. In also the cases, the models that we have trained were much better at solving sea ice concentration and flow size tasks, especially comparing to the rest of the competition. So at the very end of the competition, we decided to combine predictions for each of the tasks from the best performing models.
And we've reached the questions section. So
thank you very much. That's very impressive work with the, I thought I heard you say you had limited computing resources, but at least you run like several models. I'm very impressed by what you've done. I see that Xinwei has been very persistent in having a question for you, I guess. Xinwei, be my guest. You have a raised hand. Do you have a question to Patrick and Mikael?
maybe that's just a sign of enthusiasm. No, not really.
Yeah, maybe it's an applause.
Exactly.
It's the wrong emoji. Okay. Anybody else has a question to Patrick, Mikael? I think it's in.
I can ask a question.
Yeah. So you want to ask a question?
I can ask a question. Yes. Well, congratulations on the very nice placement and very nice presentation. From the previous presentation, we saw that they were able to improve their accuracy by downscaling the input channels, and in that way increasing the receptive field of the model. You said you had limited success with convolutional neural networks, and therefore you went with transformers. And of course, transformers, they have this self-attention mechanism that allows them to have very, very large receptive fields and perhaps even global receptive fields. Have you thought about this, or what the differences are between convolutional neural networks and transformers, and why you saw better performance with the transformers overall?
I think the major reason was because the transformer models are just way, way, way bigger. So we wouldn't be able to train a transformer model from scratch. There's just no way. The only way we pulled it off is by fine-tuning the already pre-existing huge transformers trained on like clusters of GPUs. So they have much more potential to remember all the tiny relations between the variables, right? And since we really omitted the step of feature selection and we didn't do much in terms of, well, we just used the ready to train data set. And that means that if we didn't put the work in to make the features easier to digest, then we needed a really powerful model to do this work for us and to perform in like an end-to-end manner where it's able to create all the features that it requires. And most of the CNN models that we worked with just didn't seem to be able to do that.
Okay, thank you.
You can also see that on the overfitting section. So basically, if we're not able to make our model overfit, it's just probably not big enough, because any model should be able to overfit, right? It should be an issue. If it's not, then you probably need a bigger model. And with the transformer we tried, it was really easy to overfit, which is good.
One follow-up question: which data set were the transformer models pre-trained on?
Oh, I don't really know. That comes from the authors. I mean, the deformer probably wasn't pre-trained, because that's not a transformer either, I guess. So it's only in terms of the encoder, and the encoder was pre-trained. I think it might have been ImageNet, but I'm not sure. That's to be checked in the paper from the code authors.
Okay, thanks.
Thanks.
Anton, you have a question?
Hi, very nice presentation and great results. Do you think the accuracy can be increased if you had a larger patch so that the transformer takes into account a larger context?
We tried with larger patches. 224 pixel size of a patch was the sweet spot for us, and neither the smaller one or a bigger one worked better. I regret a bit that we didn't do the downsampling trick that the previous team showed. Possibly, if we did the downsampling, that could also like make the receptive field bigger without increasing the patch size. I'm not really sure why bigger patch size didn't produce better results, because that's what I expected to. It just might be that it was like too much information, maybe. I don't know.
It's actually the same number, 256, as in the previous presentation.
No, 224.
24 or similar. Just another question for maybe not really answering. The input data, the labels, they're having a lot of errors because it's a manually drawn vector and it's not absolutely correct. How do you think what we can do with this regard? How can it be taken into account?
It's not always bad for some of minor errors to exist in a training set, I think, right? That's kind of what we do with adding noise, for example. So the deep learning networks are pretty robust to small or like statistical errors. So I mean, I'm not sure, because we lack the domain knowledge to even be able to tell whether there are errors or not. But I think it doesn't need to be perfect for the model to be able to generalize well.
Okay, thank you very much for your presentation and answers.
Thank you.
I think Andreas, you can ask a question also.
Thank you. Just a little bit of a follow-up question to that. So you added multiplicative noise to the data. So usually people working with SAR go to great length to try to remove this multiplicative noise. Did you do any comparisons of using the multiplicative noise or not?
All the augmentations didn't produce very different results. I mean, it's kind of take it or leave it. We included them because we noticed the model tends to overfit, so it's like they shouldn't hurt. And I think it was marginally better. I don't have the exact numbers now, but I think multiplicative noise helped a little bit, but it certainly wasn't very significant. And like the way of thinking behind that is that I understand that people preparing the data set went through great lengths to get rid of the multiplicative noise, but at the same time, I'm leaving like some space there, a possibility that they didn't manage to get rid of all of that. So if we introduce the multiplicative noise to the model during the training stage, it's like learns to deal with it, right?
That's the hope, at least.
Yeah.
Thank you. And maybe I also, did I hear, you had a question in the beginning of the presentation, Patrick or Michael, on something about how to select the patches for training or something like that. I don't know if that is with regards to the tools that were prepared for but I'm encouraging you to, you can put this question in the chat if you have a question for how to do that. Maybe Andreas was the person that prepared the very nice tools. Maybe we could answer that question if you if it's still valid.
Do you want to take this one, Michał?
Yeah, I think that I didn't have that question particularly. I just said that we have modified the code that we were supplied with a little bit. It was very basic, and particularly we didn't want just use random selection of those patches. So it was also a kind of method that we have used so that the model could learn a little bit more demanding examples. So we treated it also as a kind of dataset augmentation.
Okay, thank you.
Let me just add here that it's still a very naive approach that we took. Like it could be done, it could have been done much better based on the actual class fractions, like class percentages, and we took a very naive approach of just we only really took into account the percentage of water and didn't look into the actual classes. So that's like the easiest, most time efficient way to kind of help us find better patches, but it could have been taken much further.
Okay, thank you. I think we're a little over time, but anyway, I think we need we need a short break. No more questions here. Then if you have other questions, then we can include them after the last presentation. But I'll say that we break for 5 minutes now and come back at 40 past. So a small bio break, coffee break, and see you here again 40 past. Okay, thank you. At least Andreas is here. So hi everybody, are you back again here? Maybe we can just test with you, David, if we can share your presentation. You're the next. Nice.
Can you see my screen?
Yes, we see it. Great. It's 41 now, maybe, yeah, I think we can just go ahead. Thank you, David Rierstam. Try to pronounce it correctly. So you came in number 4th. That's a very nice position. Also, we're very eager to hear if your solution vary just as much as the first 2. If we have a third, very different guess on a model methodology. So take the scene. Thank you.
Thank you very much, Mathilde. Hi everyone, it's a pleasure to be here. My name is David Rijlaerstam. I'm a senior space system engineer with a company called Robotica. So a little bit about me. My background is in space system engineering. I have no background in either, well, the domain from this competition. So in AutoICE, in some of this SAR or AutoICE data, nor in AI. Yeah, I participated in the competition really to learn and to improve my own knowledge mainly in the AI field. I have many colleagues at Robotica who are experts in this field, and so I'd like to enhance my skills and try to get up to speed. And this competition was just perfect for that. So very much like to thank the organization who enabled this, and I didn't have all the time I would have wanted to because I had to participate in my free time, but I've surely learned a lot from it. It was also a pleasant surprise to be invited here. Seeing the other winning submissions was already really great. So thanks to the other competitors. I'll keep it somewhat shorter because well, I don't think my solution is as novel or advanced as some of the other teams, but I'm very happy to present some of the things that I tried and my reasoning behind it, and some of the things that worked and didn't work. So my presentation is going to consist of 3 parts. I'm going to first tell you my approach about the architecture that I tried, my training approach, and then briefly touch on results and conclusions. So in terms of architectures, I don't think this will surprise anyone. My baseline architecture that I tried was a UNet, and was really the UNet of the quick start Jupyter notebooks. For me, this, well, first of all, of course, it was a good way to get started and to get started with the data and the training pipelines that were provided. But it's also a model that's can be, depending on the backbone, can be relatively lightweight to deploy. And it's a model that within the company we have some familiarity with, because it's also some forms of UNet can be deployed on edge hardware. So we've done some work with UNet, with a MobileNet v2 backbone to perform ship segmentation on spacecraft on the edge. And similarly, we've also done some work on with UNet for cloud segmentation. So both applications can be deployed to an Earth observation spacecraft and deployed at the edge, which provides benefits for example, downlink bandwidth for these spacecraft. Now, of course, this competition is not on edge applications, but for me, it made it a good choice to get started with this model. The other architecture I have tried was DeepLab v3. The reason for that was that, well, it's for my limited knowledge and background, this is a model that performs similarly or depending on the test slightly better than UNet in certain segmentation tasks. my reasoning behind this was that it could in particular be useful to create an ensemble of networks, because potentially both networks would perform better in different nuances of this segmentation task. Plus, again, for me, this was also an architecture that I did not work for before. So again, a learning experience. So as I said, the control for my experiments was the UNet provided by the Quick Start Jupyter Notebook. For this setup, I didn't do much apart from tuning the hyperparameters. And my experiment was training a Deep Lab v3 with a ResNet 101 backbone. So that model was pre-trained on a subset of the COCA dataset. I adapted the model much to some of the previous participants. Adapted this model to accept the input shape required for this task. And I also adapted the output to the 3 channels corresponding to the SIC, SOD, and flow. And in order to get output predictions that match the size of the input patches, I used a bicubic interpolation step. So on the training, I removed the validation loop also due to memory constraints, and similarly to the previous contestants, I found that this validation loop, the results from the validation loop were not too relevant to the overall performance on the test set. So I found that this was a reasonable step to take. And one of the upsides of using the UNet was that it did allow, after removing the validation loop, it did allow for local training. So just on a laptop that we have in the office here. The Deep Lab v3 I trained on the provided Polar TAP cloud computation resource. And the settings were for the UNet were 225 epochs with 100 iteration per epoch, batch size of 32, Atom optimizer with the learning rate shown here, and I use cost entropy loss. So this is nearly the out-of-the-box quick start submission Jupyter Notebook. For the Deep Lab v3, I tried 76 epochs with 500 iterations per epoch. Of course, quite a larger network. So and with a batch size of 8. So the batch size of 8 was due to memory constraints as well. For this, I found that the learning rate had to be adapted slightly in order to for the model to converge. And again, similarly used cross entropy loss. So these are the results, and for me this was both a disappointment but also a surprise, and then it's also interesting, I guess. So my best submission was actually the tuned UNet submission. The Deep Lab submission got somewhat close, 80 versus 79% score, and the Deep Lab v3 performed better on the providing the flow mask. So while my time was somewhat limited, I did try to find an optimum amount of epochs for the training. So for UNet, I extended the training to quite a large number of epochs, which did not improve any of the results. For Deep Lab, I also almost doubled the number of epochs, which did improve the results for two of the segmentation classes, but not the overall score. So my conclusions. First one is for me personally, keep it simple. So I looking back, I would have opted to similarly to some of the other contestants, go for a network that works and improve that particular network instead of going for a more complicated solution right away. For me, I think quick iterations and a small training time are beneficial in many cases over complex and larger models. So it was simply much we simply have much quicker turnaround times for the development of the UNet than for the DeepLab v3, which made it much easier to tune hyperparameters and to spot any errors in the pipeline as well. Another conclusion for me is that in this particular test, I guess depending on the network choice, it is possible that smaller network models can perform better than larger models. And tuning hyperparameters matters. And I mentioned it earlier in my presentation. The original goal was to create an ensemble of multiple model architectures, which is due to time constraints did not happen for my submission. But yeah, my recommendation that I put in this presentation before today was that ensembles of models are likely to perform well on this task. So I'm glad that the previous presenters from PW, GSN showed that my recommendation is not entirely crazy, and I congratulate them on their nice ensemble of models. So that's it. Thank you very much for listening, and I'm happy to answer any questions that you might have.
Thank you very much, Davey. I already see questions. I see that Patrick has a question.
Yeah, a tiny one. You mentioned in your summary, nonetheless, that tuning hyperparameters matters. I'm wondering, what exactly do you mean by hyperparameters in this case?
So for me, so and correct me if I'm using terms too loosely here, but for me it was finding the right batch size, finding the right number of epochs, finding the right learning rate. So these hyperparameters for the training, because yeah, eventually, like I said, my best submission was the exact model from the quick start IPython notebook, but just with tuned hyperparameters.
And can you share with us what learning rate, for example, worked for you?
Yeah, so I think it's right here. So it's everything under the UNet training here.
Thank you.
Cheers.
I have
Okay,
a question.
thank you.
You had a total number of epochs, but you did not have a validation loop. So how did you choose the model version or model parameters that were the best? Was it just the last model or version of the model that was tuned, or how did you select that?
Yeah, that's an excellent question. You're very right to ask that question. So I'm afraid I don't have a very sophisticated answer here. So I trained a number of these models. So for a different number of epochs, and I submitted I think 3 or 4 of the units and compared the trend of the overall score. So it's not a very sophisticated solution, absolutely not. But yeah, it is. It eventually formed those submissions. This one was the best, and I'm sure that having a validation loop would would enable finding a better optimum for the number of epochs and also for these other hyperparameters. Thanks for the question.
I think I have a question from Tore here also.
Yeah, thanks a lot for the presentation and congratulations on your placement. You said that you pre-trained the unit on the COCO dataset. Did you also do experiments where you didn't pre-train and then compared the results to see what the benefit was of pre-training?
Yeah, so that's again a really good question. So the UNet was actually not pre-trained. So it was DeepLab v3 that was pre-trained.
Okay.
And so between the two, within the architecture, I did not do experiments of the results of pre-training versus not pre-training. So Again, both I took the models as is, but yeah, I would assume that without the pre-trained encoder, there would, training would just take a longer time to reach a global minimum.
Yeah. Okay. Thanks.
Thanks for the question.
Any more questions to David from the project team, expert team? Any other questions for the presenters in general? The other presenters also, maybe some questions you didn't get to answer before? I see Anton has a question.
Yeah, I have a question to all the presenters in general. You have now seen the data, you have now seen the labels, participated in this discussion. What would be the future? What can you recommend for us? Because we are developing these models further, and we try to incorporate them in operational navigation routines. This kind of advice would be really helpful.
Well, what I'm really curious about regarding this is what would happen if we took my team's model architecture and applied everything else from the winning team, because I think there may be some potential there. So I'm not sure if that's a good route, but I don't know. It seems like it could bring the score up a little bit. And by the way, a semi-question to the winning team, because you said that the unit worked best for you, and I'm wondering if, like, what are the architectures did you try? Because it's so different from my experience. That's, I don't know. I'm curious.
So I guess you are asking our team, right?
Yes.
Yes, he asked you that question.
Okay.
So my name's Javier. We tried. Can you hear me? Can you hear me? Okay.
Yes,
we can hear you.
Yeah.
Okay. We tried deeper networks, like several versions of ResNet. We also tried to generate features that were common among tasks, flows, concentration, and stage of development, but also features that were independent per task. But at the end, the results were better with a unit. On the other hand, we also tried two versions of transformers, the vision transformer and the swing transformer. But again, the major improvements were reached introducing more domain knowledge than aspects related to the architectures.
Yeah, I think compared to some large deep learning models, the volume of the data for AutoICE is still pretty limited. So maybe that's why those models like transformers do not show their superiority in this task. But if we have maybe larger data sets with more detailed labels, maybe it will show improvement. But that's future works.
And did you try to train these transformer networks from scratch, or did you fine-tune pre-existing pre-trained transformers?
No, we trained from scratch.
I think that might have been the difference. Like there's quite a lot of transfer between tasks, even if the transformer is trained on like images of like photos, it still can pretty easily fine-tune to the satellite imaging.
Awesome.
Cool. Yeah, we should try that. Thanks. So maybe we can move on to answer the question of Anton. So I think there are, of course, many directions to work on. So one of the work that we plan to do is because in the ready-to-train data set, a large portion of the polygons are not utilized for the training of stage of development and floor size because they have a mixture of ice types or floor size. So you don't have detailed pixel-based label. But we are thinking about to like directly utilize the echo information because we know the distribution within each polygon. So maybe we can develop some kind of loss function that compare the distribution of our prediction and the distribution of the echo. So in that case, we can have a metric to evaluate our results on a larger area, like from all the polygons. So maybe that will change our paradigm of how to evaluate for the CIS mapping. Maybe that's one, I think, good direction to work on.
Thank you, Shenwei. I don't know if that David has answering Anton's question. Else we'll move on to the other David, David Arthurs. You have a question also?
Yeah, I think I may be touching on the last answer, and I suspect this question is mostly directed at Waterloo, simply because I think Waterloo was the only group that didn't admit to having no knowledge of sea ice. But it's a known issue with the setup of this competition that we're considering the human analyst created sea ice charts as being the truth. And we know that sea ice charts, if nothing else, are low resolution and they probably have multiple other issues. Are we at a point where the machine learning, in fact, has exceeded the accuracy of the sea ice charts? Should, you know, if you're not getting a score of 100, perhaps that means that you're more right than the sea ice charts, and that it's the sea ice charts that are wrong rather than your algorithms. So I'm just curious as to when we reach that conclusion and try to come up with a better way of moving forward.
David, I'll bring in an expert to answer your question. That's Sun Sagan from Canadian Ice Service. Tom, we can't hear you. Even though you are unmuted, I see, but Tom, you are unmuted, but there might be something with your microphone settings on your computer. Maybe while Tom is trying to fix that, does anybody else want to address David's point?
Hi, Mathilde. It's David Clausey, University of Waterloo.
Hi, David.
Hi. This has been a terrific day. Thank you for the competition. Thank you for organizing it. We've had discussions here specifically on that question with regards to the limits of the human ice analyst and the accuracy with which they can provide an answer. And definitely they're going to have limitations with that. Oftentimes, if we're testing, we will use pixels as ground truth and pick specific pixels in multi-year or water or wherever in order to do that. But we find that we don't have enough pixels in order to generate a really good accuracy because sometimes that pixel classification doesn't really correlate with the visual interpretation of the overall segmentation or final scene segmentation, I should say. So we have conflicts going on with regards to what is the right answer is always going to be a question because SAR has its own limitations. And then I'm going to back out even further and be a little more radical here, I guess. Let's say we had no ice charting whatsoever. I mean, just say, hey, European Space Agency, we're going to start ice. We want to map ice. I don't think we'd start with egg codes. Egg codes is a legacy solution. And it was a legacy solution because people flying around in airplanes or observing from land, this was the best way for them to map the ice. But if we were to start from scratch today, there's no darn way we'd land on egg codes and use that as a modeling tool for ice. So we're caught in the past, very much like the QWERTY typewriter, right? The QWERTY keyboard, we're stuck with that forever because it was designed in the past and we use it today. I don't know to what extent we're stuck with egg codes. It's a little bit like democracy, I guess. It's not the greatest solution, but it's the best one we have. But moving forward, if we were to start this from scratch, would it be a brand new total solution? Would we do this mapping exercise differently? Would we generate results that were unique to the problem with the solutions we have today, rather than what we started with decades ago in order to do the ice mapping from aerial platforms? And really what started this is people looking out of an airplane and looking down at the water and trying to figure out what is that, and mapping the egg codes, and then people on land doing the same thing. That's where this all started from. And so we're using egg codes as a legacy solution, but I question whether or not that's the right solution moving forward. I also question, how do you pull out of this local minimum and do it a different way? That would be, that's where the radical side comes from. So I'll throw that out there for consideration. And this is nothing against all the ICE charting people, their excellent work, their dedication to creating these amazing maps that we need moving forward, because the ICE analysts are champions to me, and do a great job putting these ICE maps together on a rigorous basis, as represented by the ICE centers. That's not the issue. We're talking about the limitations of the human ability to produce accuracy, and whether or not that might need a reset. So I'm going to leave it. I'm going to hand that one off to Tom, and maybe he wants to comment further. But that's my take.
And I really want to hear what Tom says to that. But Tom, have you been able to solve your? I can't hear what you say. I really want to hear what you say. So are you able to call in maybe on the meeting, or? Yeah.
Otherwise, maybe we can take Nick in the meantime.
Yeah, maybe. Yeah, Nick. I see Nick.
Yeah, Tom types his comment in the chat or something. Work on it from there. Yeah, it really depends. It's great seeing all the presentations here and all the hard work done by different teams. And it's interesting to see the variation in the different results. Yeah, I agree that yeah, egg codes are not the most ideal thing, but they are a good way of at least summarizing what is quite a complex surface picture. Yeah, for us. Yeah, we see the limitations in the sort of generalized, sort of multi-purpose ice charts, which are produced on a sort of day-to-day basis, particularly when we're investigating sort of machine learning techniques and working with others. We try to at least come up with a bespoke ice chart or customized ice chart, which tries to address some of the issues in terms of making sure that it has sufficient resolution, sufficient level of details, and picks out the features which may be applicable to extracting with the machine learning technique. So that's kind of our approach to it. It's we realize that we need different types of ice chart to certainly train and test these types of approaches.
If I can continue on that note, I also think it's important that we remember we have scored each of these IS parameters in this competition using a single number, but there are many more. I mean, we are combining so much information into a single number, and I still think there's a lot of neurons that is lost in just doing that. Even though I do agree with David that I don't think we can get 100%, but I also think we can get closer to that mark by both ensuring we don't have typical errors where models are predicting ice where there's no ice, or water where there's ice, but also maybe measuring the models using more flexible metrics, where getting the class that is close by. I don't remember which presentation it was, but there was one of the presentation mentioning that getting the flow size, for instance, not as vast but as big, or the other way around. And I don't think maybe the ICE analysts will disagree, but they are relatively close in my book. And I also the scores that we have chosen here does not reflect that in the same way.
Thank you very much for that, Andreas. Also, very interesting topic. Also, when we're talking about building the next data sets, we consider very much what we use as label data and the amount of it, and also whether to use this also for the testing. So yeah.
Do you want the
It's interesting.
slides?
Sorry. Yeah, maybe
Do
I
you
want
want
the
the
slides. I
slides?
just want to hear if Tom's microphone is enabled. Tom, just feel free to jump in whenever you think the issue is fixed and say hi. Then we know you're there and you can get to answer the question or come with your comment. Okay. Any other questions to or comments to presenters or organizers in general? I don't see anything, but I have a couple of wrap-up slides here. I want to. Oh, maybe Nicholas.
No, yeah, I would have a question regarding the data set. I mean, some people said that size matter, but I'd like to understand what the next perspective that we have in terms of data set preparation is. That to add more information from the weather? Is that to add more sensors? Is that to enlarge, to be more representative towards all the regions in the world, like Antarctica and so on? So what's your feeling in that, or do we reach something which is sufficient to work forward? And because I guess what we have prepared is pretty consistent and quite large already. So, but do we need to do more in that?
Hello,
Yeah.
Jan. After that, please.
I can start out by mentioning that we are working on a publication of a new data set, which is more or less equivalent to the raw version of this challenge data set. This data set will consist of about 8,000 scenes instead of 500. I'm not at least able to answer the question whether we should have other kinds of data or other input data, or we should just expand the data set. But I'm sure that during the next months or half a year or something, we will be much more clever on that and be able to answer that question. And I also think I think that Tor will agree that size matters and that we will see some improvements here.
Glad to
Thank
know.
you, Johan. I'm sure that Tor agrees. Yeah, okay. Xianwei, you have a comment to that also, maybe? Xianwei and team?
It's David again, and my feedback is it possible to, instead of using dual pole, would it be possible to introduce CP, compact polarimetry, because we know from testing that CP gives us more information. I think it would increase the classification accuracy, but it's a matter of working with RCM and collecting hundreds of scenes based on CP. The complex nature of that data we know can give us a little bit more, and I think that will help with regards to someone raised the notion of specific ice typing. I think that would help in that regard, trying to narrow that down. Tom could probably comment on that too.
And I see Tom. Yeah, Tom, you have a phone now. Maybe are you able to? Maybe I can find you on the attendees list. Is that?
Allowed to talk.
Allowed to talk. Is that you, Tom? I allowed you to talk now.
There is a participant with.
Yeah, there's a new participant, and I just allowed him to talk. I think it's Tom's phone number, might be.
It's muted though.
Ask to unmute. Oh, here he goes.
I think it's working now, right?
Yeah, now it is. Good to hear you, Tom.
Okay. I'm not going to say a lot, but I just wanted to say something. And David Arthur had a very good comment about the limits of ice charts, and I've always been amazed by the data-rich environment of SAR imagery. There's so much information in there, and a lot of that information is thrown away when creating an ice chart. I mean, you just end up with a few lines. It's very important work for marine safety as a climate record, but I think using AI, we're finally approaching a lot of information. And I agree, David Clausy, that CP has a lot of promise. But yeah, ice charts are a legacy product. They came from the airborne era where people were looking at the ice from an aircraft and drawing lines. And we've kind of carried that over to this day and age where maybe it's time for a shift, a paradigm shift of actually, I mean, there's a range of flow sizes, there's a range of ice types, not necessarily bin the way that we've been binning them so far. Same with concentration. We're doing tenths, but it's really a progressive area. So maybe this is a great beginning, and congratulations to all the teams. And I think the future really is to have a lot more of that information that is included in SAR imagery brought to the mariner, brought to climate scientists, brought to everyone in terms of availability.
Thank you, Tom. Good, we succeeded. Thank you for that. I see Andreas.
I think we should let David reply first. I'll come after.
Yes. David, back to you.
Oh, that was a legacy hand that was up.
David Arthur, sorry.
I think it was the other David. It's three Davids.
David
We're back to multiple Davids. It's the story of my childhood. To Nicholas's question of what should the future hold in terms of data sets, in addition to that, and I'm not going to answer that directly, but I think we need an environment not dissimilar to the challenge, where we can continue the collaborative work and have whatever test data we choose, and it will probably evolve over time, but where people can consistently compare the performance of their approaches against some common standard, so that as a community, we can make progress on this. The problem I've identified in the past is people working in this area first are traditionally few in number, but they go off and do their own things, and we can't really see who's doing better and what works and how we could work together to do more without some common standard of an environment to do the processing and a data set to evaluate the approach.
So that would be, for example, like a benchline validation data set consisting of high resolution optical imagery or something like that, that has been with binary classification. We can do all sorts
You'll probably have to evolve, because some team may come in and say, look, you know, we found that if you add this new data type, things improve immensely. So the test data set may have to add that data type. You know, it'll evolve, but I think we need to work together to have a common standard at any point in time to compare our different approaches.
It's a very nice idea, David. Yeah, maybe, Andreas.
I strongly agree that we should have some way to, like, essentially like what the AutoICE challenge has enabled with a common scoreboard. A bit in my free time, I look at people who speedrun computer games, and they have these great websites with forums and places where you can upload essentially how well did you do on a specific game or a specific map or something like that, and then you can really get the constructive competition going where you challenge each other to beat the previous record. So I'd really like if we could have a similar environment as the AutoICE, but without a deadline for submissions, so to speak. And then the second thing in terms of data set, I agree with Jørgen and Tor. I'm really looking forward to the new data set that's coming out. And we still don't know what we can get out of that. But I also think there's potential in trying to apply some more unsupervised approaches or self-supervised, where we maybe include SAR data that doesn't have any label data associated. So I mean, we have a lot more SAR data than we have label data, I assume, in the Arctic. I also think there's some rich information that we could extract from that.
I see Shinwei. Is that a legacy hand or Shinwei and team, or is it? Do you have a question, comment here?
I don't know if some of my team members.
Everyone's using the same link, Matilda, then, so it looks like that we have Zimwei in the multiverse right now.
I'll move forward maybe to, I see that Nicholas has a question or comment.
Now, comment linked to the one from David. For your information, there are some communities, for example, the cloud from Sentinel-2 and Landsat, that federate all together and do some kind of cloud comparison, intercomparison exercise, which is called CIMIX. And I think it will be very valuable for your community to have a kind of intercomparison exercise in between the different providers. I don't know if this is the role of the ISI, I mean, the internal charting working group, but to organize that. Maybe this is up to ESA and Space Agency to organize it, but I think it will be useful on top of the platform to further the community and to have some intercomparison exercise whereby you will have some benchmark data set and so on and so forth.
Good idea. Yeah. I see Anton has a comment.
Yes, just to comment on the suggestion by Andreas that do we actually have to close the AutoICE challenge? Does it take that much resources? Can we keep it running and with the hope that the score will increase even without an award in the end?
Yeah, this is something that we can do, and we have done that in the past, and it can be open for some while.
A reason for that can be also that intern students are coming, and that's a season for intern students, and then they can help with this. And regarding my suggestions for future, I cannot avoid that as well since I asked. And regarding the reference data that we can use instead of ICE charts, or in addition to ICE charts, we have a lot of data from altimetry for laser and the radar, so we can use that for roughness, which can be much more close to what the SAR is actually seeing. So that's probably in the future can be something that we derive from SAR and passive microwave. And in addition, as input data, we can have multiple multi-temporal observations. So if we think about increasing or extending the training data set, that's something to consider. Thank you.
Thank you, Anton. I'm putting down your good suggestions, taking notes here. I'm having a hard time following what's legacy hands and what's not. Andreas, have a new hand, maybe? A new point, new?
Yes, but I forgot what I was going to say, so I'll go back in the queue.
It makes it even harder, Andreas. Sorry.
Wait, I remember now. It was to Anton. Sorry. So in regards to the current AutoICE leaderboard, so once we have the new challenge data set, I think one of the priorities is to create a much larger test data set. So this is only 20 scenes, and it's very limited what we can, how much testing we can do based on just those 20 scenes. I think we should test with 100 or 200 scenes or something like that, if maybe even more. So in regards to the AutoICE leaderboard, I think it would be at least obsolete with the current scoring that is happening there. So I think we at least need to update it.
Yeah, we need to think of that if we prolong it. Good point. Any other good points, suggestions? Else, I think we have a couple of minutes left, so I'll maybe.
The Waterloo team has a hand in the air, a physical hand.
There is a hand. I see a David Clausen hand also. So now, please go ahead.
So another suggestion as to where this is going is in regards to the final output. So the final output nowadays is the ICE charts are egg code based. However, the automated processes we're doing now, the outputs are not based on, we're not producing egg codes, we're not producing polygons. So I don't know if we want to maintain the legacy solution and be able to work with polygons, do we always want the human in the loop to generate the polygons, or is there interest in automatic generation of polygons that would then have automatic egg code parameter assignment? So if we want to mimic the legacy of the past, and that's a good way to look at maps, I agree 100%. And taking Tom's feedback into account, there's actually even richer information. Maybe we should be reconsidering some of the egg code information that involves dealing with World Meteorological Organization. But if we're going to stick with polygons as a means of communication, then we need, and we want to automate things, then we will need an automated way to generate polygons. That's a challenging problem to set up and evaluate, but I'll throw that out there as an idea.
I think that's a very good good comment, and I do agree with that.
Maybe David, is that David Arthurs? David Arthurs, is that an answer to that? Yeah.
Yeah. So there are technical issues here, and then there are small p political issues and legal issues around changing ice charts and how that's done. My organization provides polar voyage information to ships. I'm trying my best to not get in the way of how the ice services think from a legal point of view that what that information should contain. There may be a middle ground though, and I'd be interested in talking to your group, David Clousey, about other ways that automatically generated information could be used in the short term. And just as one example, we're very interested in improving automated ship routing decision support systems. And we could take automated generated sea ice information, not try to produce a sea ice chart, but to feed that data then into a route optimization algorithm, which might be a short-term win.
Tom?
Yeah, I just wanted to add that I think, because ice charts are fed into for mariners know how to calculate numerals based on those ice charts, and they look at their ship type where they can go into these waters or not. And I think we're at the stage of automation where mariners are using, calculating these numerals automatically, right, David? That the ice chart is coming in, you got your ship type, you're calculating a numeral with positive, negative, you can enter or not. So we're seeing almost an end-to-end chain of this automation. But every captain I've talked to, and I spend a lot of time in ships myself, is you want to see the chart and you want to see the image. So I don't think we're changing anything. We can still have charts, and there's a big market for that. But I think any additional products, whether the satellite image or an interpreted satellite image with AI, can be very, very useful additionally to what's out there.
I see, maybe also following that discussion, I see that Benjamin Deschamps and the attendees, I'm just trying to, Benjamin, I'm allowing you to talk here so you can ask your question or comment directly.
Hi there, thank you. Very interesting presentations and discussion. I would just add, I think one important thing to remember in terms of the big picture is the notion of technical readiness levels. And so I think we need to document very, very clearly and very carefully at what readiness level we think these solutions are, and what readiness level we want them to be to start being used operationally, because there is, like, the users of this information are facing pretty significant risks associated with the use of that information. So I think we need to be clear, or clearer, at least from the ICE services point of view, of what the bar is for a product to be produced and used operationally. And I think who's producing that product is important, how fast that product can be made available, things like that. and then also the documentation of the products and the uncertainty of the products. So I'm looking forward to seeing some of the publications that come out of this competition. I agree that the main challenge is benchmarking, and I think one of the challenges is also metrics. So I think part of the reason we're seeing high accuracies on a lot of these models is because of the selection of metrics. We're kind of very tolerant of the way we're handling large homogeneous regions of ice, and that seems to inflate the scores a little bit. So I think there's a lot of room to grow on the scientific side in terms of developing metrics that are a little bit stricter for sea ice and specific to sea ice, that focus on the transition zones and the areas where there's more heterogeneity in the ice. Yeah, so just my 2 cents based on the discussion that I'm hearing today. I won't get into the egg code discussion here. I do think there is still some unexploited information in the large database of egg codes that we have. We have daily time series in some areas, for example, that could help us disambiguate and potentially create better training data by combining existing polygons and egg codes with segmentation techniques, for example. So I wouldn't discount the large database of egg codes. I think there's still a lot of information to be exploited there. Thank you.
Good point, Benjamin. Thank you very much. Yeah, that's a good thing with ice charts also, is that there's so many of them. There's definitely data that we haven't exploited there. Anton?
Yes, it's not directly related to this discussion that we had, somewhat. I just wanted to announce before we finish the special issue in the cryosphere that is created.
I have a slide I can put on now.
Okay.
And maybe David, sorry, not David. Maybe Andreas can put on the slide, because we have, and you can talk from that, because it has some information there. If you go 1, 2 down, Andreas, not next, but next slide. Andreas, 2 slides down.
No, that one, yes.
Oh, maybe it's just my screen that is slow.
Yeah. At least I see the correct slide. Yes.
You see the correct, that's right.
Sorry for running in front of the train. Yes, so there is a special issue, and publishing in this special issue, I think, can help documenting the achievement we have done so far, and also help in documenting the technology readiness level in some way, and also pave the way for the future development. So please pay attention to that. And yeah, I also put a link to the list of the scheduled special issues in the chat, and you can find the AutoICE on this page.
And I think this information is also now, it's been updated on the AutoICE Challenge homepage. Now this information and the link to the TC submission page is there, and the deadlines and so. So we encourage you to, with all these nice solutions and methods. Maybe while having these slides on, Andreas can go 2 back. Just brief on challenge conclusions. So these were written before these presentations. So I'm just to say that from the organizers' side, we think there's been a strong participation. We are at least very happy with how many teams signed up for this, and also with the teams actually submitting a solution here, and the number of submissions and activity in general on the platform. It's been very nice to close it with this event. So we also had faces and names on those teams, and some feedback, useful feedback. So the thing was that when we put the tools and data sets available there, we didn't know for sure if they were ready to train, or get started tools, or but I guess we see from also the comments we had that they, and also from the comments today in the presentations, that these were lowering the barrier, and that these teams that presented today at least thought that the ready to train dating set was easy way in this area, also for people that didn't know of CIs before. So I think we see very good results. We were very impressed here. We've been working with this field for some time, and I see very good results from people that haven't been working with CIs for long and for a short time span of a challenge. So that's quite impressive, I think. We also see that the low scores are on the floor, and that brings up some considerations about it, whether this information is well represented in the data set and such. Maybe coming back to that discussion about using ice charts as label material and the whole partial ice concentration discussion, how to transfer this into useful information. We did some thresholding for some of the labels in the training data set, and was that the right way to do it? So we'll definitely go back and think about this for sure, yeah. And then about learnings from the participants' methodologies, I've learned a lot already for today. 3 very different methods. One UNet, one I can't say, but one sticking to UNet, one sticking to visual transformers, and the other one using the baseline model that we provided. I think it's very interesting that these very nice scores with the 3 very different methodologies. We encourage you to contribute to the AutoICE special issue that Anton just mentioned, and Andreas will coordinate an overview paper to that special issue from an organizer side, making an overview of the channels, and he'll invite you, top performing teams, to contribute to that. So we hope you will be participating, or eager to participate. Yeah, next slide. Yeah, so just to say what's next, it doesn't end here with maybe even from now we will, from this discussion, we'll keep the challenge open. I don't know, we need to discuss that. That's maybe a good idea. I just wanted to say that the resources are still there. The resources we made available to the challenge data sets are both on Polar-TEP, and they're also posted through this QR code. That's the link directly to data.dk sharing, the data platform. So you can go and they will be there. So you can go and access and do further experiments with that. And the challenge tools are also on a GitHub platform and available if people want to play with them and work with them. Then I can say that the reference data that we used for the last scoring, the scoring on the private, the additional scenes or ice charts, those will be uploaded and available together with the challenge data set collection on data.dk in one of these coming days. And then, as mentioned already, we are preparing a new training data set, and we are listening to all your thoughts and ideas. The data set is pretty much processed, so it's pretty vast. It's 8 terabytes, I think, 8,000 SAR scenes, and so far containing the same elements and data as the challenge data set. But we are very open to ideas and suggestions for how to work with these data sets and improve them. So please get in contact with us about this. I hear a lot of good thoughts about retrieval of additional information from the ice charts and so on. So please get in contact with us, and I'll put down all your comments here. But I hear you have much more to add. So and with that said, from the organizer side, I think anybody else wants to say something? Comments? Else, I just want to say, I just see Anton, but I don't know if you have anything to say. I just want to say very much thank you to the presenters and the winners, and AI for EO will get in contact with you. Now you deserve your prizes. So that you will be contacted for the distribution of your winning prizes. And thank you so much, everybody, for showing up today. I'm looking at Tor. Anything else I need to say?
I don't think so.
No? Then have a nice midday, afternoon, evening, everybody. And I hope we can get more in contact and this lively discussion can continue. Thank you.
Yeah, thanks everyone. That was excellent.
Thank you very much.
Thank you.
Thank you.
Bye, everyone. Bye-bye.
Have a great day.
Thank you. Bye-bye.
Bye-bye.
Thank you. Bye.